Okay, so welcome back. Right, Unit 2. This is going to be the last of the Newton's 3 laws of motion. After these videos, everything's going to now start looking at applications of these laws of motion. So Newton's third law, for one thing, is that to note that one thing to realize about nature is that it never produces one force at a time. So forces will always come in pairs, and we call them action-reaction pairs. Now, I may talk about this later, but I'm going to just say that right there, okay? And so Newton's third law states that for every action force, there's an equal but opposite reaction force. And sometimes when you leave the word force out, it becomes a life lesson, right? So for every action, there's an equal but opposite reaction. Now, these action-reaction forces, or as I mentioned, these pairs, are going to act on different objects, right? So basically, how do you determine what is an action-reaction pair? Well, if I have a force of object A on object B, all I'm going to do is put a negative sign, and then I'm going to flip my notation. So force of A on B is equal to negative B on A. But you can see here in the second variable, that's where the force is acting. So A is acting on B, and then in the equal one, B is acting on A. Okay. So what happens, one, is that they're not going to cancel each other out. Okay, that's very important to know. The second thing is that they're going to produce different accelerations. Okay, that's because object A and object B will have different masses. So if we go back to F net equals m times A, well, the net force is going to be these two forces, right? But object A will have one force or mass. Object B will have a second mass. So their accelerations are going to end up being different. Okay. So if I look at just some quick examples, all right, let me erase that right there. But here we got a guy pushing on a box, or a person pushing on a box. So they're pushing on the box, right? So we'll say F person on box. But what happens is that the box is going to push back on the person, right? So box on person, that's equal but opposite, right? But this person will have a mass, the box will have a mass, mass of the box, which won't be equal. And so that means that their accelerations will also not be equal. Okay. Now, action-reaction pairs are also how we move on the road, right? So my motion's going to be going this way. So my tire actually rotates here, right? And so it's going to push on the ground backwards. Okay, sorry, hit the wrong thing. And then the ground's going to push on it forward, which this interaction is going to cause that forward motion. So this is going to be F tire on ground. This is going to be F ground on tire. Okay. Now here's the fun one. Let's say we have an object, in this case, a space shuttle, right? So the Earth is going to try to pull it down, right? So F Earth on shuttle. But by Newton's third law, somewhere down here in the center of the Earth, right, it has to be an equal but opposite force, where you're going to have force of shuttle on Earth. Now, the reason why we don't see, and we definitely know that the mass of the Earth is definitely not equal to the mass of the shuttle. In fact, the mass of the Earth is much, 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 much greater than the mass of the shuttle. We don't see the acceleration of the Earth because of this great size difference. Okay. Another way to think about it is if you were to complete this Earth, this vector is inside the Earth, where this vector is outside of the shuttle. Okay. So that one appears a lot in not free response, but more of the conceptual based multiple choice questions. Okay. So let's see how this kind of will work mathematically. Okay. There we go. So here we got two canoes, right? We got one canoe is obviously going to be heavier because, canoe one here has two people. Canoe two has 4 people, but they're going to push off, right? So canoe 1 is going to push off on canoe 2, so F of 1 on 2 at 46 newtons, which means 2 is going to push back on 1 with the same magnitude but opposite direction. And so they're asking us, what is the acceleration of each? Well, that's pretty easy. So we know F net equals ma. Well, the net force is going to be what was being pushed on. So the acceleration of 2 is going to be the net force on 2 over the mass of canoe 2. And so that's going to be 46 newtons over 250 kilograms. And so we're going to get an acceleration of 0.307 meters per second squared. And it's going to be plus because you can see, here's my positive direction, right? Here's my origin. So we're going to be pushing in the positive direction. Okay, now the acceleration of boat 1, same scenario or same setup, right? So we're just going to divide by mass of 1, but the difference is the net force is going to be negative, and now we're going to have 150 kilograms. Okay, and then you can see that here we're going to have a negative 0.184 meters per second squared. Okay, I apologize, I got these backwards. So this is 1, right? And then this is 2. But this will be the positive, this will be the negative. So negative, positive. But you can see, same force, different objects. Now they're moving, right? 1, because it is lighter, is going to have a greater, in terms of the number, it's going to have a greater acceleration than 2, right? Because it is heavier. Okay, so from here on out, we're just going to look at different applications and problem-solving strategies as it comes to solving Newton's laws of motion.